course of Physical Science 110, 110. And the goal of this course is really to introduce you guys to physics and just a very broad overview of a lot of topics of physics. Um, we're going to kind of start off by uh, talking about some very interesting concepts. I want to start off by introducing myself. So I'm Devonte Kane. I'm a fifth year PhD student at UC Irvine. I will have my PhD before the end of this course. My PhD is in nanofluidics. That's where my research is, but my PhD is in physics. I have a double major in math and physics from UC Irvine. From UC Riverside, and I have a master's degree from UC Irvine. So, if you guys are interested in research or you guys are interested in math and science, I think I would be a great resource. I have quite a few friends that are engineers, um, physicists, math majors, engineers, accountants, uh, kind of STEM field stuff is my life. This is my first time teaching online. And this is also my first semester teaching at community colleges. I'm teaching at three community colleges, and I'm teaching six classes right now. So I have quite a full load. I have two children, um, six and almost two, and the 2 year old he's running the house right now. So I'm just a victim of his madness. Um, but that being said, I want to go ahead and share my screen. I want to start by going over the syllabus or just going over our Canvas website. So, in general, this is our Canvas website, and I am going to make it better. Okay. Our homepage right now is the module section, which is the main thing that you guys need to know. I think I made an announcement. And if you go to announcements and you go to the welcome announcement, I think I made the statement that you guys need to finish the first week assignments by Sunday, 11:59, and to reply to the icebreaker uh, by Friday. So the only assignment that's due this first week will be the icebreaker. So I need to actually edit this because there are no assignments for this first week besides the icebreaker. However, I said that if you do not reply to the icebreaker, you guys will be dropped from the course. So it's very important that you guys participate in the course and that I can see the department wants me to make sure that you guys are active, because if you guys are not active in the course and you guys are not actually taking the course, I need to drop you, otherwise some issues can happen. So this is not my policy. This is really the department's policy. Everything that you'll need will actually be in modules. The homepage will change to more or less a welcome statement, but everything that you need is underneath modules. And so in this first week, we're going to have just the weekly overview, which I think I have here, is that we're just going to explore physics. So, and kind of things like scientific method and Newton's laws of motion. We might not even get to Newton's laws of motion today. And that in general, I want you guys to have these learning objectives. If we don't meet them all today, that will be fine. I'll make sure to either post an additional video or we'll meet them next week for sure. This course, is an introduction to the topic, so we're not going to get like in rigor into this stuff rigorously. But in general, I want you guys to know about the concepts. And my goal as a teacher in general is to be straightforward with you guys. So I don't want there to be um, any misconception of what my expectations are from you guys. And really, there's no way for you guys to know what my expectations are unless we communicate. So watching the videos are going to be crucial to your success in the course. I promise. You cannot just read the book. You need to watch the videos and see what I'm emphasizing so that you know what's going to be on the exam. Okay? You guys will have assigned readings, and generally, I will just say, look, you guys need to have read the chapter that we're on, and we'll have discussion activities and practice activities every week. Okay? Um, okay. Okay. So let's go to modules. So right now in this first week, the only thing that we really need to have done is the icebreaker. And after this lesson, I will post the video as well as the assignment of lecture notes, which will be that you guys need to take notes on the lecture and upload your notes. And then I'll also make a discussion and a homework assignment for each week. And they will be due by 11:59 p.m. the following week. So you guys will have 7 full days of whenever the day I post. Uh, you guys will have seven. I will make sure you guys have 7 full days to complete the assignment. Questions on any of that stuff?
Nope, I think that's very clear.
Cool. Um, Sorry, you guys don't need to see people's grades. Let's go back here. I thought I clicked on syllabus. Okay, so the syllabus also I will be editing because just in terms of a syllabus, it does the job, but I really don't like the format. I'm going to try to make it a little bit more presentable and more welcoming, I guess. But this is the Zoom location of our course. This is my email, and I am live. And this is actually not even true. I'm actually live from 2 to 5 every day on Zoom from the Zoom link. You can reach me here. Here's a definition of our course, the required textbook. I'm going to tell you that really I'm going to be going off of this first textbook and a little bit of a combination of this last textbook. This last textbook is a course that is calculus based, which is not what this course is about. But it does have some concepts that I would like to go over from using algebra. So I do expect you guys to use a little bit of algebra in the course, um, on top of just knowing the concepts that we're going to be talking about. We were talking about this a little offline, and I'll make an announcement about this, but I'm going to include extra credit for coming to these meetings. I want to encourage them to be interactive because me talking at a screen I don't think it's very productive. So I know that people will have questions, and I'm really here to help people and not just to talk at a screen. I want to try to get to know you guys and help you guys and hopefully interact with you guys as well. Okay. Um, Exams are 40%, assignments are 40%, quizzes are 20%. Okay. We will probably have a quiz um, after we finish a module. So probably not today, but by next week we will definitely have finished a module. Today I'm just going to go over kind of a broad scheme of things and then get a little bit into uh, of my PowerPoint. There are going to be 4 exams given, and like I said, homework will be due the following week. I'm going to change this from Sunday to the following week because not always will I assign homework on Sunday. If I assign homework today, well, today's pretty much over, so it would be due next Saturday at 11:59 to make sure that you have those 7 full days. Okay. And look at that, extra credit already come up. I will have to edit this and say that you will get extra credit for coming to class. Here are student learning outcomes. Please do not cheat. I'm okay with you guys using ChatGPT. It is a tool. And this should say Grossmont, not IVC. I apologize about that. But I'm okay with you guys using things like um, ChatGPT to help you understand the material. I'm not okay with you guys using ChatGPT to do your quizzes and exams. I will be monitoring your quizzes and exams. And basically, during your quizzes and exams, if you leave the page at all, I will know, and you will not get credit for the exam if you leave the page. So, I hopefully that's clear. I will make an announcement about that, and I will post it in the syllabus as well. But you will not get credit for the exam if you're going back and forth outside of that tab. Okay? Okay. So that's a pretty general overview of the course. I do need to make sure that I clean this up a little bit and that I have everything on here that I need and that you guys need. I'm going to switch over now to my PowerPoint, and I guess I'll just go here. And so I'm going to start here. And please, if you guys have any questions or comments, I'll probably ask you guys questions at some point. But if you guys have any questions or comments, please ask them so that this is as interactive as it can be. But like I said, this is Physical Science 110, Lecture 1. I am a PhD. What you see in the background of this picture is the definition of the derivative, which I'm sure some may know and some may not. But really, humans invented math to be able to describe our reality. And the language of physics is mathematics. So mathematics is a language. It was invented so that we can use it to describe our physical reality. And the topic of that description, or the topic of that description is what is called physics. That is what physics is. So, in general, science or physics follows this scientific method, right? Which is the statement of the problem or what you assume the problem is. And with that statement comes some kind of hypothesis, meaning if I push this cup off the table, it will shatter and break. And the reason why maybe I think that it will shatter and break is because maybe it's made of glass. And so that's a valid hypothesis, but only by pushing the cup off of the table will you be able to really know whether it will break or not. So that is how physics works. We have a statement and we do experiments over and over again, and we look to see what happens. We go from observation and experiment to then interpreting what happened in that experiment and then testing the interpretation. And we do that over and over again. And this concept is called a phenomenology. I cannot say this word. A phenomenology. Geez, I cannot say that word. Anyway, the point is that when I write a physics equation, or I need to remember that every time I do write or look at a physics equation, it really comes from this concept that someone did an experiment over and over again, and they edited the equation over and over again, and it became eventually a law. Over hundreds of years. Some things have only been laws or theorems for 200 years, and they're subject to change. And I have this repeated for some reason right here. Uh, I don't know why that is. I think I deleted the wrong slide. But yes, the point is that in general, our equations come from experiments. So physics, and more physics. So in general, there are four major types of fields of physics. There's classical mechanics or Newtonian mechanics, which is the study of motion of large objects or objects that have a lot of energy, like me and you. We all have quite a bit of energy, and we're going to learn about Newton's laws of motion, the first, second, and third law. But yes, Newtonian physics is what really governs our everyday lives. Electrodynamics also plays a role in our everyday lives when we talk about electricity, and even our fingertips and everything are made of electrons and materials. And so the second branch of physics that was developed is called electrodynamics. And quite a few people helped develop this theory, Maxwell and Faraday. But you know, the truth is that people still are working on this topic today, right? And that it is a very nice and elegant topic. Classical mechanics and electrodynamics are two of my personal favorite topics. Statistical mechanics is probably, for me, it is probably one of the hardest to understand, but it really has to do with temperature and heat. Sorry, temperature and heat. And it has to do with the molecules in the room somehow relating the kinetic energy of a single molecule to the temperature of the entire room. So, statistical mechanics or thermodynamics takes the very small and tries to relate it to the many, right? So, one particle trying to relate the energy of one particle to many, many, many particles, the properties of many, many particles. And it takes a lot of math and probability to be able to do this well. We will just touch on some very basic properties of the physical systems. Probably for sure the coolest one, I guess it's kind of up to you, right? But quantum mechanics. Quantum mechanics is the study of maybe like electrons and particles. And those objects, those single particles really have very small amounts of energy, right? Those systems that only contain a few particles have overall very small amounts of energy. And in that realm, very weird things happen, things that we do not experience at all. For example, if I throw a ball at this wall over and over again, I know it's always going to bounce off of the wall and come back to me. And there is, and this happens. People have taken, I think recently there was a Nobel Prize won for the application of quantum tunneling. But quantum tunneling says that you can bounce a particle off of the wall over and over again. And every once in a while, the particle just goes through the wall. And it's not that it tunnels through the wall, it's not that it makes a hole through the wall. No, it transports through the wall. It does not exist in the space of the wall. It hops from one side of the wall to the other without ever going in between. And this concept was really probably, so I've been doing physics for maybe 10 years. And I would say maybe around year two or three, that's when I first learned about this. And this was probably the most crazy and interesting thing to me, right? That how could a particle go from one side of the room to the other side of the room without ever touching the middle of the room? And this happens all of the time. This is a real thing about physics. And to me, it was like, wow, so transport is possible. What else is possible? So these are the four major fields of physics. This is what, I've devoted my life to up to this point, at least the last 10 years. So I'm 31, at least the last 10 years of my life has really been devoted to this. And kind of this is where uh, my passion lies. I also love helping students. I've been tutoring for about that long as well. And I think helping people in general is part of who I am. So I want to give you guys who are here a second to really ask any questions that you might have on these topics, or if you have any interest, if you want to have a conversation, or what you think. Okay, so we don't have many people here right now, and maybe they've stepped away. But this topic right here, these topics right here are uh, the major topics of physics. Oh, we have a chat. Oh, no questions so far. This is my first time ever learning about this topic. It's all very new, and I'm a bit nervous about it. Oh, don't be nervous, Jasmine. We're here. We're excited. There's no there's nothing to be nervous about. This class is really just an introduction. Um, I'm not trying to make you nervous at all. I'm really just trying to get you excited and interested in some of the really cool things that happen in physics. Okay, so I pulled up the chat. Now do I exit, I guess. Okay, cool. Okay, let's keep going. Yeah. Okay, so one of the first things that people did was that they actually studied the sky. And so here, this is an example of what we mean by physical laws come from experiments. So what we're looking at here in this picture is actually an experiment that has been taking place for a very long time. And maybe not a very long time relatively, but maybe over 20 or 30 years, the telescope has captured the light from the sky. And what we're seeing here is actually over a period of time, the tracing of the light from the stars. So maybe I can hit um wait, can I turn to a pointer? Yes. So you guys should be able to see this pointer. That means that every single one of these lines is actually from a star, and that over time the star has moved. And so it's like all of the stars are moving around the center of this point. So the center of this point is the North Star, which is the center of our Milky Way galaxy. So everything that we actually see in the sky is actually moving around this point or this location. Just like how we're moving around the sun. It's very interesting and it's very cool to see that from an experiment we can really tease out our reality. Let me get rid of the pointer. Okay. And so what I just have here too is this is a more modern experiment, but at the bottom I have Kepler's laws of motion, which tell you that the path of the planets around the sun are ellipses with the sun at the focus. And the planets move so that the radius vector sweeps out in equal areas in equal times. So this is not something that I want you guys to know yet. We might do a problem on this in the future, and I will maybe, if we do a problem on it, I'll post a 5 to 10 minute video explaining it in very good detail. But this is just an example on one of the earliest things that humans have done really has been to study the sky. When Isaac Newton invented calculus, he invented calculus to be able to describe what he was seeing in the sky. And Galileo was well before Newton. So, okay, well, we're talking about the sky and what we see. Well, maybe we could talk about gravity a little bit. Gravity might be a natural way to go here. And so, what is gravity? And gravity is a force that we all experience every day, right? And so, really, what is a force? A force is a push or a pull. And so, what we feel is we feel the earth pulling on us. If we jump in the air, it tells us to get back down, it pulls us back down. It's always pulling on us. And most people think that gravity is an interaction only between the earth and themselves. But that's actually not true. We'll talk about it in a little bit, what mass is, but any two objects that have mass actually experience a gravitational force in with each other, and that the more forces that act, that there are more forces that act as part of the fundamental forces of our universe. So it's not just gravity, right? And here I have posted the equation of gravity, that the force of gravity is equal to some constant, like 5 or 10. This constant is not 5 or 10, but I'm just saying it's just a number. It's a gravitational constant times one mass times the other mass divided by the distance between the masses squared. And so this equation, and I want to stop right now. Hopefully I can get some responses, but I want to know if you had to solve for M2, could you guys solve for M2 in this equation? Can anyone just tell me what the answer to that is? I'll give it a second. And so if you're watching this video at a later date, which most of you will, I want you guys to make sure that in your lecture notes, I will specifically be looking for this. I want you guys to solve for M2 in this equation. I have Fg is equal to big G little m, or big G M1 times M2 over R squared. I want you to solve for M2 in this equation. I want to know that you guys can do that. If you guys can do that, then you guys have all of the math that you need to be successful in this course. Okay, Jasmine? You mentioned that you were nervous, and hopefully that kind of clarifies expectations for the course. Okay, so I'm going to move on. So we said that it's not just gravity, that there are actually more forces that act on us. And there are four fundamental forces of the universe. There is the gravitational force that we feel because we have mass. There is the electromagnetic force that charges feel because they have charge. And then there's the strong nuclear force and the weak nuclear force. And these things specifically have to do with atoms and molecules. And we can read about them. The strong nuclear force holds protons and neutrons together inside the nucleus. And it's the most powerful force, but it acts at very short distances. While the weak nuclear force causes types of radioactive decay and nuclear reactions. And it is only at short distances within the atomic nucleus. these two forces we might talk about a little bit, but in general, all of these forces we should be talking about at some point in this class. And we just want to just kind of learn about them and learn maybe some of the experiments and some of the results from the experiments that have happened with these forces. Okay. And so again, we have a better definition of the different types of forces, gravitational force and the electromagnetic force. So for example, on an exam or on a quiz, I would ask you, what is the gravitational force? What is the electromagnetic force? Or maybe I could give you a multiple choice question where I tell you this is an attractive force between any two objects that have mass. And maybe part A is gravitational force, B is electromagnetic force, C is strong force, and D is weak force. So my point is that I do want you guys to be able to distinguish between the definitions of the four types of forces. So we have gravitational force, electromagnetic force, and a gravitational force, it says that gravity is the attractive force between any objects that have mass. It is what causes objects to fall towards the Earth and keeps planets, moons, and satellites in orbit. And gravity becomes stronger when objects have more mass and are weaker at distances between and it becomes weaker as the distances between them increases. Okay? So it is the weakest of the four fundamental forces, but it acts over a very large distance and it plays a large role in shaping the universe. The electromagnetic force is an object that acts only between objects that have charge. So if two neutral objects interact with each other, they will not have an electromagnetic force. It includes both electricity forces and magnetic forces. And maybe we'll see a little bit of that electricity and magnetism are actually one. You cannot have one without the other. And that it is responsible for many everyday phenomena such as electricity, magnets, light, and chemical bonding. This force controls how electrons move around atoms and how atoms form molecules. Like gravity, it can act over long distances, but it only affects charged particles. So, a more clear definition of the strong nuclear force is that the strong nuclear force is what holds protons and neutrons together inside the nucleus of an atom. It is the strongest of all the fundamental forces, but it only works over extremely short distances, about the size of the atomic nucleus. So very, very small. The nucleus is maybe, we'll get there. We'll get to kind of scales, how big and small things are. So without this force, atomic nuclei would not be stable. And we have the weak nuclear force. So the weak nuclear force is responsible for certain types of radioactive decay and nuclear reactions. It plays an important role in processes such as beta decay, where particles inside a nucleus change type. Like the strong force, the weak force only acts over short distances. Okay, so we kind of talked about these things called distances, and maybe we want to be able to understand what a distance is. What does that mean? And to really get into what that means, we need to get into units and measurement in physics. So what is a unit? A unit is a standard measurement and it's used to express a physical quantity like time, a unit of time, a unit of mass, a unit of length. Those are three of the big units that we'll be covering in this course. Time, mass, and length. Okay, so the metric system. The metric system is based off of powers of 10, and it uses prefixes to indicate multiples of a base unit. So I have another graph on a future slide about this, but basically we will need to learn how to convert from kilo to centi, from centi to milli, and so on. So probably after this PowerPoint is over, which it should be over, we only have a few slides left. I'm actually going to give a little bit of a talk about my research, which my research is actually at the nanoscale. And so this is stuff that I've been doing over the last 5 years. And if you guys are interested in it more, we can always talk about it. So all of the units uh, have an SI unit. So for example, the SI unit of length is the meter, but you can also have centimeters, you can also have inches, but as a as a as a collection of human knowledge, we usually use the standard of SI units, but really it depends, right, on your system. So for example, it would not make sense for me to use meters. It wouldn't because I work in nanometers at the nanoscale where things are very, very small. And so it would not make sense for me to use meters in any of my calculations. I always use nanometers. And once again, I've just said that the three major units of the physical quantities that we'll be talking about are length, mass, and time. Those physical quantities uh, act as a fundamental platform for many other physical quantities, and we'll see that. Okay? And so, like I said, we will have some problems. I will post a video after this specifically covering converting units. So this is one of our objectives in this class is to be able to convert units. It will probably be part of your homework assignment to convert units. Okay, and this is that table that I had mentioned where, hey, we have nanometers, picometers. I think that most atoms, the radius is on the scale of picometers. But we also have nanometers, micrometers, millimeters, centimeters, and there are many more. You have to know whether you're getting smaller or whether you're getting larger. So if the power is negative, then you're getting smaller as the power gets more and more negative. But if the power is not negative, if the power is positive, then you're actually getting bigger and bigger as the power gets bigger and bigger. Okay, so a few of these, maybe I can do my pointer again. A few of these that are very important are going to be micro. Micro is a very important one that I suggest you guys know. Milli, centi, kilo, and mega. Those are the most common ones. Mega, kilo, centi, milli, and micro. And right now, maybe this is your first time seeing this, but I definitely will go over problems where we're converting units and and problems that have these sub have these prefixes so that you guys can get familiar with them, as well as their abbreviations and names. This is a very useful table to have. Okay, and so this is the end of my presentation for right now. I want to talk a little bit about my research. But yes, right now there are only 4 people here. And so I'm going to go ahead and stop. I think we've done enough for this session. I will post another video and encourage people to come again. And I will go over in that video about units and whatnot. And it will be next week on Friday. So today was just a broad overview of physics, all of the four different types of physics, which is quantum mechanics, statistical mechanics, and electromagnetism, and Newtonian physics. Those groups of physics try to describe all of the reality that we know exists. That is the goal of physics, to describe all of reality. And, we've gotten pretty good at it. We have one single equation that can describe all of reality, except that one equation is extremely, extremely messy. And we suspect that it should be a bit cleaner. Um, and we haven't got into any topics of energy or motion yet. All we're talking about is units. I will post another video about units, and we will continue to talk about motion and energy later next week. So at that, I'm going to stop sharing.